It's great to be joined today by Alex Filippenko, professor of astronomy at the University of California, Berkeley, and the only person to have participated on both teams that discovered the accelerating expansion of the universe in 1998. Let's start there. I think that this is a concept that even at its base level can be difficult for the average person to understand. How is the universe expanding and expanding at a faster and faster rate? What does that even mean? Is the universe contained within something? How is it measured? Give us a sort of layman's term introduction to the topic.
Wow, David, that's a lot of material. So we know that stars live in galaxies. For example, our own sun is in the Milky Way galaxy, which is a collection of more than 100 billion stars gravitationally bound together. And there are other galaxies out there, billions of them. And when we look at distant galaxies, we see that they're moving away from us. We can actually tell this because their light is shifted to longer wavelengths. It's redshifted, and this tells us that space is actually expanding between us and the other galaxies. So if you extrapolate this backward in time, you come to a time about 13.8 billion years ago when it all began in a very dense compressed state, a point we call the Big Bang. And it's been expanding ever since. But the galaxies are pulling on one another, just as, say, the Earth pulls on an apple that's thrown up. And so the apple slows down because of the gravitational pull of the Earth. And so we would expect the expansion of the universe to be slowing down because of the mutual gravitational attraction between all the galaxies. Well, about 2 decades ago, two teams set out to measure the rate at which the universe is supposedly slowing down in its expansion, to see whether it'll someday stop and then collapse in a big crunch, or continue expanding forever, although progressively more slowly with time. That would be eternal expansion forever, but more slowly with time. And what we found surprised everyone. Instead of slowing down, the expansion of the universe has been speeding up, as though it's driven by some sort of a repulsive effect, which we call dark energy. So that was the big news in 1998, and we and others have been trying to figure out what is causing this acceleration ever since.
Okay, so many follow-up questions, and I'll pick one to start with. Uh,
Sure. Yeah.
Conceptually, could this expansion be infinite? And I know infinity is sort of a concept in and of itself that is a whole other rabbit hole for using a term that has no particular meaning in this conversation. But if it could be infinite, how is that possible? How could we even understand that?
Right. So, there are two possibilities for the universe. Either it's a finite volume universe, and there think of an expanding balloon where hypothetically the universe is just the rubber, okay? And you can travel along the surface of the rubber, but you can't go inside or outside. So that would be the expansion of a finite, closed, two-dimensional space into a direction which is mathematically describable but physically inaccessible to anyone on the balloon.
Hmm.
Okay, so that's a finite universe expanding into some higher dimensional hyperspace. Okay, but you could also have an infinite universe, and I think this is what you were talking about. And it's confusing. How can an infinite universe expand? Well, think of the number line 1, 2, 3, 4, 5, and 0, -1, -2, -3. Suppose I were to take every 10th number, 10, 20, 30, 40, 50. That goes on to infinity as well. But in a sense, it's less dense, right, than 1, 2, 3, 4, 5.
Yeah.
Or I could take 100, 200, 300. That goes on infinitely far as well. But again, it's even less dense. So you can have the number line expanding, or if you take just specific numbers within the number line, there are fewer and fewer of them, but they still go on forever, if you know what I mean. So an infinite universe can expand. It just becomes less dense with time, just like this number example that I gave you. But it's not expanding into anything. It's just expanding. It's not becoming more infinite because it's already infinite, just like the number line is infinite. but it's becoming less dense. And these are difficult concepts around which to wrap your mind.
Yeah, you're telling me. So this gets me, the
Yeah,
balloon example gets me to something that has sort of bewildered me as a kid, and I've never really even had a good way of sort of thinking about it. What's outside the universe? Is there, so talk to us about some of the thinking around, well, if we have something that is more in the style of the balloon that you're talking about, where is
yeah,
the balloon, so to speak?
right. So, the balloon would be our three spatial dimensional space, X, Y, Z, and it's expanding through time, T, the fourth dimension, into a spatially distinct dimension. You could call it W or something. So it's sort of like the balloon, you can go forward and backward, left and right, or any combination of those two motions. Equivalently, if you use what's called polar coordinates, you're moving in theta and phi, two angles. But you can't yourself move into the radial direction toward the center of the balloon or out of the balloon into the bigger radial direction. You can mathematically describe that dimension, but you cannot yourself physically access it or point to it.
Hmm.
But mathematically, it makes sense. It's just a higher dimensional hyperspace. So in our case, if we live in a three spatial dimensional universe wrapping around, quote unquote, a fourth spatial dimension, then we're expanding into that fourth spatial dimension. But I can't tell you where it is. I can't point to it. I can't grab it. I can't see it. It's mathematically describable, but physically inaccessible. And so you can think of it as just a higher dimensional hyperspace.
Okay. Let's pause
If
on
that
that
helps.
train of thought. Now that
Yeah.
we've cleared that up and I have like a really good understanding of it, let me ask you, as a general, you're very, very good at, as people have seen so far, taking very complex concepts and sort of breaking them down into their fundamental parts to at least help us to start to understand them. When
Oh, thank you.
you, in whatever experience in the world you have, and this could be from media, from talking to students, whatever, what's one of the biggest misunderstandings or most common ones that you see the average person has about space or the universe or our world that you like to be able to clear up? What's something that you find
Yeah.
is commonly coming up that people are sort of not understanding?
Right. Yeah. Well, certainly it's the idea of the center of the universe. We tell people that we see all the galaxies moving away from us. Does that then imply that we and the Milky Way galaxy are the center of the universe? And in fact, it doesn't, because imagine an expanding loaf of raisin bread. And the raisins are the galaxies. And by the way, they don't expand because they're held together by gravity quite strongly. But then you have the dough, which is filled with yeast, and you let it sit for an hour, and let's say it doubles in size. Well, if you put yourself on one raisin, you see all the others moving away. And so you say, whoa, I'm at the center of the universe.
Hmm.
But then you call up your friends in some other raisin, and they say, well, we see everyone going away from us, and so we're the center of the universe. And then to break the tie, they call up a mutual friend on some other raisin and they say, well, you guys are all wrong. We're at the center of the universe.
Hmm.
But here you can see that because of the uniform expansion, no raisin, no galaxy can claim to be at the unique center of the universe, even though to each of them, it looks like they're at the center.
So Trump
So there
Tower
is
on
no,
Wall Street is not the center of the universe. You can say
no, that's right.
unequivocally.
Exactly. And, you know, it's because of this uniform expansion that each of us thinks we're at the center, but there is no unique center, at least not in dimensions that we can physically probe. Now, going back to our balloon universe, that one does have a center. It's the center of the balloon, but that's not part of the universe as I've defined it. The universe in that case is the rubber balloon. Similarly, if we live in a three-dimensional space that wraps around a fourth dimension, then the center would be in that fourth dimension, but that's not part of our universe. That's in this higher dimensional hyperspace.
One thing I like to ask when I interview people working in astronomy and space exploration, et cetera, and I've had some interesting conversations with Lawrence Krauss about this, is your sense
Yes.
that we will ultimately come to some complete understanding of the origins of the universe that goes orders of magnitude beyond what we have now? Do you see that as a sort of point in the future?
I don't actually. I think we'll get to a better understanding than we have now, just as over the past few centuries, by this amazing process of science, we've come to a better and better understanding of nature. And we come up with equations that have good explanatory power and predictive power. But I think, in terms of a true, ultimate, complete understanding of the origin of the universe, I personally am skeptical. And it's because fundamentally, we can't, as far as I can tell, definitively test any hypothesis that we make, right? When you ask what happened before time equals zero or at time equals zero, you can come up with various possible answers to that question, but how do you test those different answers, those hypotheses, without creating new universes? And even if you do create new universes by some method, how do you know that's the only method and therefore was the one that created our universe?
Hmm.
The uniqueness idea is something that can't really be tested, right? The uniqueness of an explanation. So I'm not saying that I don't enjoy physics. I clearly do, and I think people should continue pursuing these questions. But there may be some questions which are ultimately not answerable by the human mind, even with the most experiments and observations that we could possibly make.
Hmm. Fascinating. We've been speaking with Alex Filippenko, professor of astronomy at the University of California, Berkeley. Thank you so much. Really fascinating.
Thank you.